So the first question I missed was asking about how we could determine that the inertial momentum, the initial mass, rotational inertia of a rod was 1/3 mr squared. So to do this, first of all, you would start with I equals the integral of the radius squared dm. So what I did wrong here is I used P where the density, which we shouldn't use unless it's 3D. So we should have used just lambda, which is lambda equals m over L. And then if you cross multiply, you get L lambda equals m. And then you can basically do differential related rates and do dl lambda equals dm. And then when you plug this in, you'll get I equals square root of lambda r squared dl. And we could basically just change this r to an L because the r in this scenario the radius is the length, and this would be from actually yeah, that would be the answer here. So then what you would do next is that you would take the integral of this, which is equal to 1/3 because you're doing the power rule, lambda because lambda is a constant, and then you're going to do r cubed, or L cubed, sorry. So then when you plug back in lambda with what we have up here, m over L, you'll find that you get 1/3 m over L, L cubed, and these would cancel out to 2, and you would get 1/3 ml cubed, which is the answer it wants, what it wanted us to find. So then for the next part, for part B, it was asking derive an expression for the velocity of the free end of the rod at position B. Express your answers in terms of m, L, and physical constants, and you may not use any energy. So this means that we need to use torque. So the first thing that you do is you're going to do that at your equations, which is F equals, or torque equals F force times radius, and torque is going to equal rotational inertia times alpha. So if you set these equal to each other, so if you solve for this first, you'll find that this is going to be equal to mg, which is the thing, which is the gravity force, and then your radius is going to be L over 2, and then you're going to set that equal to inertial mass times alpha, which is ml cubed alpha, or that would be 1/3 and this 2 is a separate thing, so like that. And then next what you're going to do is you're going to set them equal to each other, which you can do over here. And that's a squared over here. Yep. And then alpha. So then what you can do next is you can basically just solve for alpha, because that's the only unknown in this equation, or like the only, that's what we're basically trying to solve for. The rest are constants. So if you solve for this, you get alpha equals 3g 2l over 2l. So now that we have this, we can basically just use kinematics, which we have to do in the question because we can't use energy. So first of all, what we're going to do is we're going to use equation 5, which is this, and there's no initial angular velocity, so you can just leave that part out. and then theta. So now what we can do is we can just multiply this out, and we get omega equals the square root of 2 times what we got here, which is 3g over 2l. And then finally, we're going to multiply by pi over 2. And now these two are going to cancel out, the 2's, and we're going to be left with 3g pi over 2l. And then finally, what you're going to do next is you're going to just see that v equals omega r. And then you're basically just going to divide, by, or you're going to replace omega, and then, well, you actually don't have to factor anything. You can just leave it like this. So you put in omega, and you get the square root of 3g pi over 2l. And then you can replace the r with an L, because that is the thing, so it would be looking like this. And that will be your final answer. And then the next question asks you to list what you would put out to get the velocity, or sorry, to get the graph. And for this part, you would probably want to simplify. So when you simplify this out, it would be v equals root 3gl. And so basically what we can see is that we have v on one side, and then we have root l on the other side. So those would be our two quantities that we'd want. So on the x-axis, we'd want the root of length. And on the y-axis, we would want v. And then I do this on a separate, I already do the graph to save time. So this is the graph. And basically, yeah, we have length here, and the units are in square root of meters and meters per second. And this is the line of best fit. And then, so the next question asks to correctly calculate the slope of the line. So to do this, what you can do is, first of all, you can just find 2 points that look easy to calculate. So I chose these 2 points. And when I did that down here, I got 5.333. And then what you would do to calculate the slope is you would use this equation, which is basically what we found here, because the slope is root 3gl. So we just setting that equal to root 3g. And then when you solve for that, you find g is equal to 9.4815 for this line. And then 2 ways air resistance could be reduced is that, one, they could use a more aerodynamic design, so that there's less air resistance, but the inertial mass is still spread out. So they could probably just use a thinner rod. And then the second option could be something like I'm doing it up at like a higher altitude, because that would also, like, there's less air up there, so that would also be another option. So then for the next question I missed, which is after the FRQ, it asked, a uniform bar is lying flat on a table if, besides gravitational force and normal forces, the bar is acted upon by 2 forces which are parallel to the surface of the table. So that means that they would be like this. If the net force on the rod is 0, which of the following is true? So if the net force is 0, that actually means that they're on opposite sides. So it would be like this. So basically, if the net force of the rod on the rod is 0, which of the following would be true? So if the net force would be 0, that means that they have to be on opposite sides. So if it was something like this, then they're so what I initially said is that the net torque on the bar must also be 0. But the thing is, so if it was something like this, the net torque would not be 0, because this force is going to be they're pushing the same direction. They're both pushing clockwise. So the only situation where the torque would be 0 is if they were applied at the same point and they cancel each other out. And then that would let the torque be 0. So the next question I missed was asking about basically a bar that had 2 torques, or 2 masses. And one mass was 3m over here, L, and then this one was 2L, and it was just M. So what I did wrong here is that I messed up and I didn't correctly calculate the torque, the rotational inertia. So I is equal to the sum of the MRs. And in this case, that's going to be equal to 3mL squared plus 4mL squared. And that's because this is 2L, which is, when squared, it's 4L squared. So that's going to equal 7mL squared. So then what you can do next is you basically have the sum of the torques, and that's going to equal L, and this is just F times R. So it's going to be F, well, it's going to be your first one, which is L, times 3m0 g, because that's gravity. That's your force, and that's your R. And then you're going to do minus 2L m0 g. And then this is, in total, it's going to be m0 gl. Now, the next step is that you're just going to set this equal to t equals IA. And then that's going to go to these two equal to each other. So you have m0gl equals 7m0 L squared A. Or alpha, not A. And then when you solve this out, alpha is going to be equal to G over 7L. Okay, the next question I missed was this question, which asked basically whether it had a disc and a ring going up a ramp, and that's which had the highest height. And basically, based on so what actually happened is I thought that it was asking which one would go fastest down the ramp. So I said the disc will go farther, or move. I thought it said move faster instead of. So initially I thought the disc would move farther. So I was wrong. So I read the question wrong. But by the if you think in terms of energy, the ring has a higher has a higher moment of inertia, so it would basically be harder to slow down, and hence, since they're both moving at the same velocity, the disc would go higher because it's harder to slow down. Or the ring, sorry, not the disc. The disc is solid, but the ring has a higher moment of inertia because the ring's moment of inertia is 1/2 mr squared or the disk's moment of inertia is 1/2 mr squared, and the ring's moment of inertia is mr squared. And then the next question I missed was asking about basically a bar that looks like this, and it's on a hinge like this, and basically it's asking what the acceleration would look like. So the only acceleration, like the angular acceleration here, would be gravity applying a torque. So the thing about gravity is that it would be greater and greater. So we're looking at a graph where the end point is higher than the beginning point. And there's only two graphs like that. There's one that goes like this, and then one that goes like that. And the thing is, gravity, like the angle is in either cosine or sine, one of those. Like you could think it through, but you don't really have to because they both have the same shape, which is this little sinusoidal shape. So it would be that. And then the last question I missed was basically one of the questions where the sine is hanging. So what you should have done for this problem is you should have done the sum of the torques, and you know that it equals 0. And then there's three things. So what I did wrong initially is I didn't think about the weight of the beam from the center, because gravity always acts on the center. So the weight of the beam, and you should have done L/2, not L like I did initially. And the sine, which it gives you the distance to the center of the mass of the sine, which is d, so you don't have to do anything for that, plus ft L sine theta. And this tension is at the end, so you don't have to do anything for that either. So then basically you can just solve this out by putting the other two on the other side. So you get ft equals mass of the beam g L/2 plus m sine gravity times distance over L sine theta. And when you solve this out, you'll get 108.989. And you have the G here because this is the weight, where the force, we're doing force times radius up here. So this is the force and not just the mass. And yeah, that's it.